Hello, my name is Muhammad and I'm going to talk about BCD and Windows boot process. In this presentation, I will go through the main stages of Windows boot process and how BCD fits in, what are the advantages of using BCD comparing to anti-LDR. We'll learn more about MBR and what is boot sector, followed by a live demonstration by extracting the MBR code from a live machine and inspect the MBR code piece by piece. We'll show you how to access the system BCD store and how to perform common tasks related to BCD, like enabling the serial console, enabling the crash dump, or boot into safe mode. In the last module, we'll explain Windows Serial Console and how BCD makes it possible on Azure Windows VMs. Let's begin. Booting or bootstrapping the operating system starts from the second you power on your VM or PC until you see the operating system logo loading on the screen. During this time, 4 main stages happens in the background. In the first stage, the BIOS does the power on self-test against all the attached devices and initialize them. Once that's done successfully, the BIOS reads the MBR code from the first attached disk or storage device and load that MBR code into the memory. The MBR code in turn loads the boot sector from the designated boot partition. Then finally, the boot sector loads the kernel. Let's talk about each one of the stages in more details. In the initial stages of the boot, the system can use only limited resources, as the bootstrapping works in chain loading method. Each process passes information to the new process and give it the control. This allows the new process to utilize more computing and storage resources and continue the boot. The first limitation with multi-CPUs or multi-core system, after the motherboard initializes the hardware, it chooses only one CPU to run the initialization codes. This chosen CPU is called BSP, Bootstrap Processor. Once the boot process completes and loads the kernel code into the memory, it can activate all the remaining CPUs. Another limitation, which related to the computing as well, is the processor mode. When the boot starts, it runs in real mode, and it stays at that mode until the operating system kernel takes over. Real mode means that the CPU can only address 1 megabyte out of the physical RAM. And the reason for this was the only mode that the early Intel processors were capable of. At this stage, the motherboard has chosen which processor will execute the BIOS code, but how the CPU will know the address of the BIOS code in the memory. This problem was solved by the reset vector. Reset vector, it's nothing more than a standard location address in the memory. It's the default location a CPU will go to find the first instructions it will execute after a reset. This location contains a jump instruction for the CPU to the BIOS code location in the memory, and once the CPU executes it, the post diagnostics will kick in. Now at this point, the BIOS code got loaded and executed along with the post test, which means the hardware is healthy and it can proceed with the boot process. The next stage is reading the MBR, which is the master boot record from the first configured storage media. We'll assume in this presentation that the media is a locally attached hard drive. Each drive is divided into tracks. The sector is a subdivision of a track as shown in the picture here. Typically, each sector is 512 bytes in size. The data which contained in the first sector, which is 512 bytes long, is a well-defined and is called master boot record, or for short, the MBR. The MBR code is neutral, meaning it could be a Windows MBR, Linux MBR, or it could be even a virus. 2 slides before, we talked about the reset vector and how it's a standard memory location for the BIOS code. There is another well-known memory address which holds the bootloader code, and it's located at 7C00 to 7DFF. The MBR is constructed from 4 pieces of information. The first part is the MBR or the bootstrap code. This code main function is to load the bootloader from the selected operating system. The second part is the disk signature, which used to determine which disk the machine will boot from. The third part is the partition table. It's for the primary partitions only. The last part does have multiple names: MBR signature, boot signature, or the validation check. This value is used to confirm the integrity of the MBR data. Multiple boot records does exist on the disk, one for each partition and one is the master. The one which holds the map for all the other partitions is called the master boot record, and on each partition there is also one boot record. For example, this disk have 2 partitions, C and D. The total boot records here on this disk will be 3. One is the master one for C drive, and one for D drive. This is the hexadecimal data of typical MBR. The first part is the MBR code or the boot code as shown here. It's from here to here. All of these data is for the boot code. Then it comes the partition table. It's from here till here. The partition table contains the status of the partition. Is it bootable like the second partition here, or non-bootable like the first partition here? You can see the starting head, sector and cylinder for this partition. Where is it located on the disk? Then the partition type, the value is 07, which means it's NTFS. The third partition is empty. The fourth partition is empty. Then the number we talked about for the validation check, it's located here, the last 2 bytes. Next up, we'll check the MBR data on a Windows VM running on Azure. We'll do a live demonstration now and extract the MBR data from the OS disk on a VM running on Azure. I'm going to use the PowerShell to extract the MBR data from the first attached drive, which is the OS drive. And we'll do that using a module available on the PowerShell called PowerForensics. This module provides rich commandlets for hard drive forensics analysis. We'll begin by installing the module as it's not available by default. Let's begin. We need to run PowerShell with admin privileges. Install Forensics Module by typing install-module space PowerForensics. Approve the installation for the required packages. And since I know the provider of the module, I'm going also to trust the source of it. You can see how much this module is powerful by examining the commands which this module provides. Let's continue with the MBR data extraction. To list all the attached drives on this VM, you can run WMIC disk drive list brief. Let's check the disk signature for the first attached disk, physical drive 0, by using the command get forensic boot sector. The disk signature was introduced by Windows, but it's now used by several operating systems, including Linux kernel version 2.6 and later. Windows uses the disk signature as an index to all partitions to any disk connected to the operating system. Starting with Windows Vista, the disk signature is also stored in the boot configuration data or BCD, and the boot process depends on it. If the disk signature changes or cannot be found or has a conflict, Windows will be in no boot scenario. Now let's get the complete MBR by using the command get forensic master boot record. Give it the path of which disk you want to get it from. We'll get it from disk number 0 as it's the OS disk. And as bytes switch parameter to return the raw bytes of the boot sector, and pipe it to format hex function so we can read it. Now we are looking at the MBR data for disk 0 in hexa and ASCII code. Let's first confirm the magic number or the validation check value at the last 2 bytes. It always must be 55AA for a working MBR. Here is the disk signature. The partition table starts from here. 80 means it's bootable partition. 20 is the starting head location of the first partition, and here is the starting sector and the starting cylinder, etc. And each partition table entry is 16 bytes long. Also, you can redirect the output of the last PowerShell command to a file and examine the MBR data using a proper editor. Coming back to the boot process, due to the tiny size of the MBR, which is 512 bytes, the MBR code loads another code, and this additional code contains more specific info on how to load the operating system itself. With Windows operating system, the MBR starts Windows Boot Manager, or for short, Boot MGR. Then the Windows Boot Manager finds and starts Windows Bootloader, or for short, WinLoad, on the Windows Boot partition. In case multiple operating systems were detected on the machine, Windows Boot Manager displays a boot selection menu similar to this in order to choose which operating system you want to boot from. We used to see this selection menu whenever the system boot in Windows 7 and before, but now with Windows 10 it's disabled by default. If you enable it, we'll see how to achieve that in the labs at the end of this presentation. You will be able to enter the advanced boot options, for example, by pressing F8. In either cases, if you choose which system to boot from, or in case you didn't, once the timer expires and this timeout is configurable, Windows Boot Manager loads the bootloader, then the bootloader loads the operating system kernel, ntoskernel.exe. This file is located under System32 folder on the system root partition. Keep in mind that Windows Boot Manager can also load other operating systems, meaning not just Windows. For example, if you have Linux and Windows 10 installed on the same system, the boot manager displays the menu to choose which OS to boot from. If you select Linux, the boot manager hands over the boot process to GRUB bootloader. Before Windows kernel and NT 6.0 version name Vista, the Windows boot process was handled by a former bootloader called NTLDR. This bootloader was using a file which contains the boot parameters and settings, and it was called boot.ini. In Windows Vista and later, winload.exe has substituted NTLDR. Once winload got invoked by the boot manager, it searches for the operating system kernel. The boot manager does this with the help of the boot configuration database, or BCD. BCD is a database registry file. It contains the boot configurations and parameters. Those configurations controls how the system boots, and you can easily customize them, which will be reflected on how the system boot. We'll examine some of those settings and the use case for them in the labs at the end of this presentation. BCD registry file is a binary-based file, not like the former bootloader boot.ini, which is ASCII based. Although this could make boot.ini easier to deal with, but BCD is more powerful, and it provides an abstraction layer at the bootloader level. Interacting with the BCD can be achieved via the GUI, or the command line interface. The command line interface provides a one-stop for all the BCD settings, not like the GUI. On the other hand, the graphical user interface provides access for the most common settings for BCD. Those settings can be accessed via msconfig under boot tab or startup and recovery settings. Let's examine them both together. Using run, type msconfig and go to boot tab. You will find here a subset for the BCD settings. For example, if you want this VM to boot into save mode on the next boot, you can check save boot. We talked before about the timer of the boot menu. You can configure the timeout value from here. The other place, which also have another subset of the BCD settings, is the startup and recovery settings, which can be accessed by right-click on my computer and choose properties. Click on advanced system settings. Under startup and recovery, click on settings. Another way is to use run box and type sysdm.cpl. Here you will find the crash dump related settings, what type of crash dump you want to collect, full memory dump or minimal, or if you want to change the location of the crash dump file. Before we start the labs, we'll go through some of the terminology used with BCD. BCD store is the binary file which contains the BCD settings and configurations, and it also called the BCD registry file. This file is typically located under the system reserved partition. For example, this VM is running on Azure. We have two disks by default, one for the operating system and one for the temporary storage. In order to access the file system for the system reserved partition, we need to assign it a drive letter. We'll use the letter E. Now I can browse it using File Explorer. As this partition have system protected files and folders, you need to show the hidden and the system protected files and folders. Open boot folder and scroll down or press B on the keyboard. Here is the system BCD store for this VM. Boot application is a boot environment application, such as Windows Boot Manager and Windows Bootloader. To view the content of the system BCD store, type bcd edit /enum. The output shows the two boot applications for this system, Windows Boot Manager application and Windows Bootloader application. There are more boot applications included in the system BCD store. To view the full list, you need to type the same command but add all at the end. There is a globally unique identifier, GUID, for every boot application, and there are well-known identifiers like bootmgr for boot manager and current for the current booted operating system. You can use those identifiers with the BCD commands to declare which boot application you are targeting with your command. This is a globally unique identifier, and this one as well. This is a well-known identifier for the boot manager, and this one for the current booted operating system. Now we will utilize the BCD in order to deal with some real-life scenarios. The first scenario we are going to examine is enabling the serial console in Azure VM. On Windows VMs, the serial console is possible because of the Emergency Management Services, or for short, EMS. What is the serial console first, and how we can enable it, and how we can do that online and offline. By online, I mean doing the changes on a booted system directly, without specifying the BCD store location, as it will be applied to the system BCD store by default. In the offline method, you need to specify the location of the BCD store by using store keyword. This happens, for example, when you have a VM with no boot scenario, and there is no way to send any command to the guest operating system directly. In such scenario, you will take a copy from the faulty VM OS disk and attach it to another working VM, and made the changes there in the rescue VM. You can access the serial console of a VM by clicking on the VM blade and scroll down to Serial Console. This is a VM which was created from Azure Marketplace, and any VM created from the Marketplace will have the Serial Console enabled by default. After waiting a few seconds, you should see a ready event message saying the CMD is now available. Type CMD so the EMS can open a channel with the CMD of the VM operating system. The event message says we have channel number 1 ready for the CMD. In case you opened multiple channels, you can list all the open channels by typing ch space -l. Channel number 0 for serial console, and channel number 1 is opened for the CMD. To connect to channel number 1, type ch space -si and give it the open channel number. Press enter. Provide the credentials. Now we are connected to the guest operating system command line interface. You can execute some commands like showing the version of the system, who am I to confirm the current logged in user, and also examine the IP configuration. Let's assume this VM is migrated from on-prem. First, let's check the EMS configuration on the system BCD store by typing bcd edit enum. Remember that in order to have a serial console working on Windows, you need to enable the EMS in the system BCD store. The Emergency Management Services is disabled on this system because EMS is set to no under the bootloader. This is because it's disabled under the boot manager. To enable the EMS, you need to set it to yes under the boot manager application. We'll use the well-known identifier for the boot manager, boot mgr, because I'm targeting the boot manager application. Along with enabling the EMS, we need to configure the port and the baud rate. At this point, the system is ready to accept Azure Serial Console connection, but we need to reboot the system in order for this change to take effect. Now let's open the Serial Console for this VM. Wait for a few seconds. Here is it. The CMD is now available. We can follow the same procedure we talked about to access the guest OS command line interface. What we did was enabling the serial console online on a live system. Now I will show you the offline method by listing the BCD settings on an attached OS disk copy. We'll attach the disk first to the rescue VM here from the disk blade. This disk will be listed as data disk inside the rescue VM. Open Disk Management to inspect the disk's layout. Disk number 2 is the attached OS disk copy. We'll open the CMD with the admin privileges so I can access the system BCD. As discussed before, the system BCD store is located under the system reserved partition. It already have a drive letter, which is E. To access the system BCD store for the attached OS disk copy, we need to add the keyword store and the path for the BCD store under the system reserved partition E. You can use the same command structure for any other command in case you need to change any value for the system BCD store. Next up, we'll show you some of the common settings for the BCD. There are some other scenarios for changing the system BCD settings, like for example, if you want to connect your system to a WinDBG machine for debug purposes. Basically, we will do the same change as we did for the serial console, because the debug will utilize the EMS. But the additional command is to enable the debug. Another example is enabling the advanced boot menu, so you can boot from last known code configuration, or to choose any other option from the list of the advanced boot menu. You can also use the BCD to enable save mode booting or in case the system keeps booting into the recovery mode, you can disable this behavior from the BCD. Sometimes if you perform a lot of changes to BCD, or in other cases the BCD file got corrupted, you can easily recreate the BCD by using this command. But keep in mind 2 points. 1. Before you proceed with that, make sure to rename the old BCD file to another name, so you don't end up with 2 BCD files. 2. Some settings like the EMS for serial console are not enabled by default. Thus, you need to make sure to re-enable it back again after you recreate the BCD. I will also share a useful link with you. I have many examples for common BCD settings, so you can keep it as a reference. By this, we have reached to the end of this presentation. I hope you learned a few things by watching it. Thank you for listening.